Well, hello. Welcome to the Infrared Training Center's webinar, Calculating the Return on Investment for a Condition Monitoring Program. I hope you enjoy this and I hope you learn from it. I'm Ron Lucier. I hold an ASNT NDT Level 3 in Thermal Infrared. I'm a senior instructor in the responsible Level 3 for the Infrared Training Center. My educational background is as a mechanical engineer. I have over 40 plus years of infrared experience, and 25 years of that has been with Teledyne FLIR. And currently I'm the chairman of the ISO Technical Committee 108, Subcommittee 5, Working Group 11, which is infrared thermography, under which condition monitoring falls. What is condition monitoring? Well, it's a continuous process of evaluating the performance of a system with a goal of early detection of anomalies that could affect the performance of that system. Your doctor performs condition monitoring on you by physical examination and testing. Condition monitoring specialists assess the operational condition of machines via infrared thermography, lubrication, vibration, motor testing, ultrasound, and many other technologies. Now, there are several distinct steps to a condition monitoring program. The first is data collection, and then after that, data analysis, and then alert generation. What is of concern from that data analysis? Also, planning on how to deal with the alerts, how to get things repaired, and always looking for continuous improvement. And the above are just as appropriate for a human as they are for a manufacturing plant or a power plant. The ideal condition monitoring program would be created at the same time a facility or system was constructed. However, that rarely occurs, so condition monitoring programs are generally established from existing systems and equipment. So what is condition monitoring? What is the condition monitoring process? Well, the first step is to assess the condition of a system or of a plant. And one of the things we have to answer is why do we want a condition monitoring program? And this is where we would set our goals. We're here to increase production, reduce costs, increase reliability, things of that nature. And then we want to identify our resources. What do we have available to us? Do we have to start from scratch, or do we have things that we can draw from? And also, do we have any concurrence from management? Explain to them what the reason for a condition monitoring program is and why we want to invest in it. So once we've done the assessment, we want to do the planning. And during the planning stage, this is where we would establish a budget, identify personnel that are going to be monitoring the program, managing the program, doing the inspections and reporting. There's a whole bunch of folks that are be involved in this. And then we want to select alert criteria. In the example of thermal infrared, maybe we want to use the NFPA 70B criteria, or we establish our own electrical criteria for our unique applications. Or we're going to go into the industry and say, what does everybody else use? What other standards are out there for electrical, mechanical, vibration, all of these other applications? And once we have our criteria, then we can sit down and write the inspection procedures. The inspection procedures are critical. If you don't have a good inspection procedure, how are you going to know whether your program is being implemented properly? So this is where a bunch of time comes in, is just making sure that we have everything written down that we want to do, and keeping in mind that this whole condition monitoring plan here is just one big circle. So maybe in the future, once we start to implement our inspection programs, we want to change them. Okay, so it's not like you create an inspection program and you're stuck with it forever. Then what we want to do is we want to invest. Maybe we have to invest with inspection equipment. That can be very large capital expenses, or that could be very minimum. Perhaps we have some things that we can use already. And then we need to invest in personnel, make sure folks get the proper training. We make sure we have folks with a proper work ethic. And this is one of the more important things. And of course, when we're investing here, we have to do this with the concurrence of our management, with the concurrence of our customer. Once the investment phase is over, we implement it. And this is where you get a lot of learning. The best way to start a condition monitoring program is to perform baseline inspections. What do these components look like today? And at some point in the future, we'll be able to compare with them so we can see what has changed. And that's a critical step that many people miss. They'll start up a program, they'll just start looking out, doing their inspections, electrical, mechanical, vibration, lube oil, ultrasound, etc., and not really knowing where they are in the life cycle of a component or a system. So it's really essential that you perform a baseline inspection. And fortunately, there's plenty of software out there, like the FLIR Thermal Studio, that can assist you with, route planning and just creating a database of your results. And then during the implementation, this would be where we identify our initial anomalies. Doing our baseline inspection, perhaps we find something that's vibrating out of spec, or we find an electrical connection that's hot, or a bearing that's hot. And in doing this, we're also going to be performing corrective maintenance. Now, the corrective maintenance is also fed back into here. Has the process correctly identified what the anomaly is, what the issue is? Okay. And then the next step here is to monitor. We're going to track our successes and failures. Not all programs are 100% perfect when you start them up. Perhaps you have the wrong personnel, you have the wrong technology. And so we want to evaluate our personnel, we want to evaluate our process and refine the program, and then we go right back into that assessment phase here. And that is basically the condition monitoring program. You assess, you plan, invest, you implement, you monitor, and you just keep going and going and going. Now, what is return on investment? That's a financial ratio used to calculate the benefit an investor will receive in relation to their investment cost. The above is simple to understand for stock, bond, and mutual fund investors. However, that definition might not directly apply to condition monitoring. The investment costs are simple. How much money invested in technologies, purchases, salaries, and overhead? That's easy to quantify. It's the benefits that become very difficult to quantify. But there are some useful metrics. Now, ISO 9001 establishes a standards for quality management systems, and most companies make a decision to get ISO 9001 certified based on their internal return on investment calculations. And that's what the Infrared Training Center did, and Teledyne and FLIR many years ago in implementing the ISO 9001. It wasn't just done because others had done it, it was done because there's a positive return on investment. Now, with our condition monitoring, there's usually some driving force for creating a program, or purchasing inspection services, another way that this could be implemented. They can include code requirements, perhaps such as NFPA 70B in the United States, and that requires annual inspection of electrical components, and there are some caveats there. There might also be regulatory requirements, and I'm more familiar with the Environmental Protection Agency requiring condition monitoring of oil and gas producers. There could be some insurance company requirements where the insurance company says, hey, we want to reduce your risk, and we want to reduce their exposure to any potentials. And so the insurance company and risk reduction, they go hand in hand. And you might have a history of component or system failures that you just want to monitor. You want to find out something that's better, a better way to operate or a better way to design. And also how to optimize the process, looking at our process. Where are we losing heat? Where are we losing energy? And there's also peer pressure, and don't discount that, okay? Peer pressure. The facility over in the United Kingdom has created a really good condition monitoring program, and they want us here in our country to do the same. And so that's the type of peer pressure, okay? And there's no one size fits all for any company. Everybody has unique goals and challenges. All right, so the cost, how do we quantify the cost? And these are sometimes easy to quantify, but it takes a little bit of planning. The initial cost would be equipment purchase, and the expenses, cameras and vibration equipment and acoustic equipment. They need regular maintenance, repair, and or calibration. There may be some instances where fixed installation is more important, where putting a camera or fixed vibration probes And that might take a little bit of extra engineering to do. And of course, there's other tools, for inspection. And then we have our labor, salary, benefits, overhead, our management, training of the personnel, and planning, and maybe you need additional supervision for the program. This is all in our costs. Now the benefits. These can be very difficult to quantify. So there's no one recipe that fits everything. There are tangible and intangible benefits. Tangible means things that we can quantify, and they include a lower cost of production. Perhaps you have conveyor belts, and conveyor belts have some rollers, and those rollers are hot. And so by making things more repairing things appropriate, lubricating things appropriately, your electrical energy goes down. We'll see a case history of that. Okay. Increase system and component reliability. Well, that's the whole goal of any program, is increase our reliability. Maybe we're purchasing components that aren't best suited for our application. So let's identify and find a better component. Reduced equipment damage, very important. Once you fail a component, it doesn't necessarily mean that a replacement is readily available. And then increased life of the system and or component. Motors and pumps and shafts, they're all very, very, very expensive. And by a good condition monitoring program, you can actually extend the life of those components. And the whole thing here is to get to early detection of failure. Okay, we want to make sure that if things are going to fail, to get an idea of when, so we don't have to have extended outages waiting for repair parts. And working with our insurance companies, lower insurance rates, and that it can be a very, very significant amount. Now, the intangible benefits, those that can't be quantified, can include early identification of preventive maintenance program failure. What we mean by that is identifying when things are starting to go wrong, when components start to fail or processes start to not be as efficient. And then there's goodwill and the reputation of the company itself. Okay. Now, this is one of the most important ones, the early detection of failure. It's a hallmark of a mature condition maintenance program. There may be some future time where condition maintenance programs aren't identifying any failures. They're not seeing any anomalies. And there is anecdotal history of management wanting to cancel or defer CM inspections because there were no reportable results. This is very short-sighted. If you're not finding something with your program and you've got all the technologies out there, the infrared, thermography, the lubrication, the vibration, the motor testing, etc., that is confirmation that you have an excellent preventive maintenance program. And the condition monitoring program will tell you right when that preventive maintenance program starts to go sideways. Okay, and this is something perhaps we need to communicate to management. Look, we're the vanguard out there looking for when things are going bad. So it's critically important to continue inspections, as they will identify emerging maintenance and or operational issues, or maybe even component issues. So switch to a new type of component and it starts to fail. To put a dollar number on that is almost impossible to quantify, but it's something we really need to understand. Now, what is goodwill? Goodwill is the hardest benefit to calculate. And definition of goodwill: the favor or advantage that a business has acquired, especially through its brands and its good reputation. There are many, many MBA cases presented every year on companies who did something wrong and lost their reputation. They lost their customers. And it's very, very hard. It's very hard to get a customer. It's very, very easy to get rid of a customer. Okay, you can lose them very easily. And so, I'm not going to get into the details here, but there's lots of case histories, and I'm sure you will recognize some things that might even be current in wherever you are. Okay, so a good example of this would be a manufacturing plant supplying a part to a just-in-time manufacturer. That supplier's reputation would be positive and very good if they deliver all the required parts on time with excellent quality. Not so good if they have frequent production shutdowns that cause delivery delays. And so, by not having a good program, you might uh, do a lot more goodwill damage and reputation damage than you might think. Okay, so that's a good way to avoid it. Now, how do we calculate return on investment? That's the core of this webinar here. And over the years, we've been able to identify three ways. It's called direct, the value, and avoided costs. And the avoided cost ones is we're going to spend the most time on because that's the most complicated. And I'm sure there's others. Individual companies may have a better way to do this. But all of those, the direct, the value, avoided costs, they have one very important requirement. It needs the approval and endorsement of your management or your customer. Okay, and your management is your customer in many situations. Okay, so we have to get some buy-in. So the direct method. The direct method is commonly used when evaluating an insulation project. Assume that a heated product must be stored in an insulated tank before processing. The annual cost of heating that tank is $4,000. The cost of re-insulating the tank is $30,000, but will reduce the heating cost to only $1,000 annually. Therefore, you have a $3,000 per year savings, not accounting for inflation and the price of energy, of course. And so that's a 10-year payback. And some people will say, well, maybe that's a little too long, and others will say, well, hey, it is an investment. But another good example might be easier to quantify is replacing incandescent or fluorescent lighting in an office building with LED lighting. The cost, the materials, labor, disposable are easy to calculate, and as are the net savings in electricity. So that's what we would call the direct method. Okay, here's an example of an electrical direct method. The actual heating dissipated from an electrical connection can be very small. Most of the motor control centers, lighting panel connections, they're 1 to 10 watts worth of power. And so if you're just finding 1 or 2 or even 10, it's really not that large of an economic loss. But in this situation here, that's a 98 degrees Celsius connection, and it's calculated to be about 150 watts of power, and this was at a generating plant. Okay, and so they, rather than putting that power down the line, it's being dissipated to the environment, so it's a loss. If we assume that the power plant makes a profit of 6 cents per kilowatt hour, and I have no idea what the profit is on power plants, that's just a number, that's $130 per year in lost revenue, which is, there's no economic reason, there's no direct reason to repair that. And you wouldn't even see that in the balance sheet of the power plant. However, if that progresses and gets worse, there could be a bushing failure, which is a much larger issue. So that's just one example of a direct method. Okay, here's a direct method of a mechanical situation. This is a roller bearing on a conveyor belt. The heat dissipated due to the bad bearings was calculated to be 24 watts. And there were 162 similar bearings throughout this facility. So 162 times 24, that's 3.9 kilowatts of dissipated heat. Not really per day, but dissipated heat, and that works out to be about 34,000 kilowatts or 34 megawatts of heat. That's a lot of heat. Okay. And if we assume 80% efficiency, power motor, bearing, belt, and I don't know what the efficiency would be, that's probably pretty optimistic. And with a power cost at 25 cents a kilowatt hour, that's about $10,000 a year in extra electricity costs. So just by having a good lubrication program, that facility could save a substantial amount of money. Okay, and you can scale this up, you can scale this down, and there's numerous ways to calculate how much heat is dissipated in an individual component. Okay, now the value method, very interesting. This was the method presented several times at the Infrared Training Center's information conference. We held that conference from the year 2000 to the year 2018. Unfortunately, it's no longer held. But this paper that's referenced down there is a wonderful paper, and it was presented by the insurance company CNA. and they classified problems. They take their infrared cameras, they go out to their insured properties, perform the infrared inspections with a goal of reducing the risk and preventing failures. So it's an advantage to both companies, both the insured property and the insurer. And over the years, they came up with some relatively arbitrary values, and they said a minor problem and an intermediate problem, it's worth $500, okay? And a serious problem, that's worth $3,000. Now, those are very, very, very conservative, I'm sure. But it's amazing how much money that you can save. And you can see the temperature differences that they assigned. They had their own categories. Okay, and that's wonderful. This is what they use. It's very, very successful. And they estimated that each survey cost of the insured property about $500, but saved $2,000. We have a 4-to-1 return on investment. And they also added an energy saving cost as electrical connections dissipate heat, that's wasted energy. And it's a very, very, very simple method. And I believe from reading the paper, over a 10-year period, they saved over 20 million US dollars for their insured companies this way. And I believe that it's probably very, very conservative. And here's an example of a fictitious company, and what the little side note there says total 322 components were inspected over a 2-day period, 11 minor, 2 intermediate, 1 serious, and 4 critical. And just 100, 250, 1,000, and $2,500 were assigned to the minor, intermediate, serious, and critical for a total value savings of $12,600. If you can get your company or your customers to buy into something like this, it's reasonable. They can see the value of the program, okay? And that's the whole idea behind the value method. Now, here is the complicated one. This is called the return on investment avoided cost method. And this is very, very detailed. And there is an Excel spreadsheet that accompanies this webinar, okay? Now, this method has 2 assumptions. The probability that something will happen, good, bad, or indifferent, is 100%. I don't know of any other exceptions to that. And number 2, something would have happened, one of the above, if the component was never inspected. So that seems kind of confusing, all right? But all components and systems will eventually fail. This might take minutes, seconds even, or thousands of years. The failure may be inconsequential, or it may be catastrophic. Prediction of time to failure in failure mode is very difficult, but something will eventually happen. And there are costs associated with number 1 above, okay? And the costs associated with inspecting or not inspecting are likely different. This really answers the question, what would have happened had we never inspected that component? That's another way to think about that. And in order to discuss, to understand this, we have to understand probabilities. And this is what's called the bathtub reliability curve. And on the y-axis, on the left-hand side, that we have the probability of failure. And it's just an arbitrary number from low to high. And then we have time on the x-axis, okay? And so over a period of time, this is how, in particular, electronic components will this is how they work, okay? So there's a brief period of time called infant mortality. And for illustration purposes, I made it a large, kind of a large number there, but things have happened when you first buy something like a toaster oven and you turn it on and it just fails immediately. It fails the first time it turned on. That's infant mortality, and that's usually the manufacturers taking their data, their failure data, and then determining a warranty period. Okay, not for every manufacturer, but that's in general. But but once things get operated and they get lubricated and things get burned in, etc., you get into a normal operation situation where the probability of failure is fairly low, but it's not zero. Okay, and as things wear out, we get to the end of life where the failures start to go higher and higher. And this is just a typical curve. And so the useful life of a component can be different. It could be based on the quality, the application of the component, the service of the component. So this is just a theoretical curve, okay? But it illustrates some basic data, okay? Now, it's a generalization, doesn't apply to every system or component, but it's just a good way to understand why reliability might not be constant. And there are some very extensive programs, the reliability-centered maintenance programs that track components for reliability. And they have two large metrics, MTBF and MTTR. Now, MTBF means the mean time before failures, and that measures the average time between failures for devices needing repairs. And you can find some data online as to the typical MTBF for a motor or for a cable or for a pump, but they might not be for your application. The MTTR is the mean time to recovery. That measures the time necessary to get something repaired and bring it back into service. And this might be something that an individual program might want to start to track, particularly if you're just starting up a program like at a brand new facility. So these are statistical metrics that large utilities and manufacturing companies may track, and some do publish their results. I'll leave that to the observer here to go track that. Now, there's a lot of public resources for MTBF, but the best data set would be one developed by the individual organization. So let's assume a motor has a 20,000 hour MTBF. It may fail earlier than 20,000 operating hours or later. That's one of the unknowns. But if that motor operates 40 hours a week for a production facility, 50 weeks a year, so it's got 2,000 operating hours, the mean time between failure would be 10 years, and that would be information very important to a planner to know that, hey, we just put this motor in place, and at some point in the future, we ought to start thinking about having a replacement. But then there's everything like Murphy's Law, if something can go wrong, it will, and chaos theory that interrupt these MTBFs, and things fail and way sooner than you think, and then things last a lot longer than you would ever expect. So these are just averages, these are just the means, okay? So the mean time to recovery, that seems to be the easiest metric to calculate. Most organizations can reliably estimate the labor and materials cost from most repairs. But what if the repair requires a new component? There's a new component in stock. Is one available from a plant or distributor? Does a new component need to be built? And so over the years, the inventory in individual companies and utilities has gone down, and they don't have stock rooms full of parts for everything. A large utility-sized power transformer might take 24 months to build if one is destroyed and no suitable spare is available. And so there are things that take an enormous amount of time to build, and that would affect the operation of a facility. So when a failure occurs is also important. Is it on a holiday weekend? Is there sufficient maintenance personnel available? And there's lots of intangibles, things that we cannot quantify that are available with MTTR. But it's one of the, if you have a good history, if you good data on your repair crews and how effective they are, it should be a little bit easier to get a handle on that. Now, calculating avoided costs is one way to quantify the value of a condition monitoring program. It should answer the question, what could happen if the inspection repair was never performed? In other words, you ignore your condition monitoring program. How do we assess that? Okay? The process is straightforward for manufacturing, as the cost of production, labor, and materials is sometimes easy to determine. This can be adapted to utility power generation as well, but the cost of replacement power can be determined, but that's a function of time and day and source, and so that becomes much more difficult. MTBF is used to help estimate the failure probabilities. MTTR is used to help estimate the repair and recovery times. So this is the avoided cost process. You identify an anomaly, you describe it. And the process that I've been using for over 30 years is to determine things, the best case, the medium case, and the worst case. And we'll get into this a little bit detail, okay? We calculate the repair costs for our best, our medium, and our worst case. We calculate our production costs for the best, the medium, and the worst case, okay? And then we get everybody to agree, and this is a really important part, okay? This is usually where there's a lot of agreement between maintenance, between management, between the inspectors. We know the best case would be nothing happens and it gets repaired, okay? The medium case is we have to take an unexpected outage to repair it. In the worst case, it fails catastrophically. So once you get an idea on your descriptions, your repair costs, and production costs, everybody agrees. We assign probabilities. This is where a lot of disagreements happen. So once you assign what is the probability? Your gut feeling that, yeah, we're going to make it to our next repair outage. What's the gut feeling for the medium, and what's the gut feeling for the worst case? And this is probabilities. Now, probabilities range between 0 and 100%. Nothing can have a probability less than 0%. Nothing can have a probability greater than 100%. Okay? That's a 0 to 1 thing. So what you do is you total and multiply each case by the probability. So we take all of our costs for the best case and we multiply it by the probability for the best case. And we take all of our costs associated with the medium case and we multiply it by the probability of the medium case. And we do the same thing for the worst case. And keep in mind the probabilities have to add up to 100. And we sum the fractions, the fraction of the best, the fraction of the medium, and the fraction of the worst case. And does everybody believe the results? And if they do, hey, we're all happy. Or no, we're not. And if it's no, you go back up to here. Usually it's the probabilities. You might have management say, yeah, we can make it till next August. And you might have the maintenance engineers saying, no, the last time this happened, it failed in 1 week. And this is where you just go back and forth through the probabilities. And then you end up with what's called an avoided cost. And that's the process here. Now, let's go in detail. And again, there's an Excel spreadsheet. And it will be available with this webinar. And the spreadsheet is designed to answer what might happen if this component had never been inspected. Now, in general, the best case scenario, the component does not get worse and it gets repaired during regularly scheduled hours. Okay? Medium case, the component continues to get worse, it gets hotter, it vibrates more, and an unscheduled shutdown is needed for repair. And number 3, the component catastrophically fails and affecting other equipment and maybe even production. And that's our worst case scenario. And it's important that we describe these in detail, okay? So there is a 100% chance that something is going to happen. The best case, the medium case, the worst case. So be very descriptive, okay? You may need input from technicians, electricians, mechanics, engineers, planners, suppliers. Systems are very complex, and a group decision is less likely to be criticized if it's wrong, okay? Identify if parts are in stock or not. Lead times for those parts and other issues are very critical. Like how long does it take for something to cool down before you can do maintenance, all right? And be practical. A 15 amp breaker in a lighting panel is unlikely to detonate, causing massive destruction and casualties, okay? And so this is where a lot of interface, particularly with electricians and mechanics, is important. What will happen if this fails, okay? So be very reasonable on this. So your case anomaly scenario, be very detailed. The management and customers might not understand the component or system, so you have to describe it to them. And if you don't, find somebody who does. Find an engineer, find an operator. What does it do? What will happen if it fails? Are other components, system, processes affected? Is there another pump that could be swapped out because this one is failing? And this is a good time to add previous history if available. Okay, describe what happened the last time that component failed, if it did. And so this is what the avoided cost worksheet looks like, and this is a blank one, okay? And the first thing to do is to describe each scenario, and you can add, this is an unlocked Excel spreadsheet, you can add very extensive details. So we're going to describe each scenario. What's the best case? What's the worst case? What happens? And once we have the scenarios described, we have to go and fill in important information like how much time did it take to diagnose this? How much time was involved in management, repair, cleanup hours? These are the things that either have occurred or are going to occur. And we sum up our total labor hours, and then parts. You can put as many parts in here as you wish. You can expand this Excel spreadsheet as you need to. And is there any production hours lost? Was there any business interruption? Is there a case where we have to pay somebody because we couldn't make that product? Okay. And so that becomes very important. You do this for the best case, you do it for the medium case, you do it for the worst case, and it'll sum everything up. Okay. And then we have to add in labor rates, our management costs per hour, maybe engineering costs could be a separate one, labor costs per hour, production costs per hour, environmental cleanup costs per hour if that gets involved. There may be many that are involved here. Okay. And then we assign the probabilities. If you think it's 100% probability you're going to get to the weekend in repair, we'll put 100% in there, okay? But rarely is it 100%, catastrophic failure or, medium failure. It's usually, there's some probability that it's going to either get worse or catastrophically fail. But this is the unknown, and this is where the flexibility of this technique really works, okay? Now, here is a sample calculation. We see electrical over here because we're the infrared training center. And so we see that there's a cable here that is stranded, meaning some of the strands in the wire, whether it's broken or not, are just not connected. Some of them are carrying more current and others are not carrying any current. And this is a case history from something that happened in my past when I was a consultant. A commercial bakery produces thousands of loaves of bread per day with their 100-meter long gas-fired oven. That's a continuous process with about 3,600 loaves of bread inside the oven at any time. The bread takes about 30 minutes to bake, so the oven bakes 7,200 loaves per hour. And each loaf of bread costs the bakery $1.12 to make, bake, and package. So that's their total cost. And I don't know whether these numbers are correct or not. It's just a sample calculation, okay? So let's say this is $8,064 per hour of production cost, including overhead. And the thermographer wants to know this particular component there was supplying the power to the conveyor belt, bringing all of these loaves of bread into the oven. If it fails, if that goes open before it gets repaired, the conveyor belt stops and everything inside burns. Okay, so that's our case description. Now, the best case scenario: the bakery has a scheduled shutdown in 5 days. The conductor does not increase in temperature and only the cable needs replacement. And that seems to be reasonable to me. Okay. Medium case, the breaker was looked at again at shift end. The temperature had increased significantly. An unscheduled shutdown of the bread line is required. The breaker and cables are replaced, and fortunately everything is in stock and the personnel are available to do the repairs. A worst case scenario, the cable fails catastrophically shortly after the problem was discovered. The failure causes the conveyor belt to stop, burning all the loaves inside the oven, and they have to be disposed. The breaker, starter, cables, cabinet have to be replaced. There's a 48-hour shipping delay for the breaker as they don't have one in stock. Okay, so I could think of other things that would be a worst case scenario, but this is, I think, pretty reasonable. Now, in a lot of manufacturing, they have business interruption insurance. What happens if we can't make a product? And so I added this in here. The bakery has insurance that will compensate a customer that depends on their production. This includes a major grocery chain that sells an average of 14,000 loaves per day. Again, arbitrary numbers. The insurance starts 24 hours after the failure. The profit on each loaf of bread is 66 cents for a total loss of profit of $9,240 per day. And the insurance company will pay 80% of that and reimburse the customer, usually $7,092 per day. And I don't know whether this is reasonable or not, but it seems to be fairly common. Okay, so the first thing here, we describe our issue. The second thing here, we describe our scenarios, our possible outcomes. And the third thing is here, we identify anything that's unique to know. Maybe if something fails as an environmental loss, something goes into a river, something goes up into a stack. So there could be many, many things happen here, but this is the process. I describe our cases, we describe our scenarios, and anything else that would be good to know. And then we start to plug that into the value, into the spreadsheet here. So this is a very, very simple sample calculation. Our maintenance, best case, maintenance schedule, and that's our best case scenario. And so we add all of this up here, arbitrary value. Hey, 85%, I think 85% chance that we're going to get to the weekend and we're not going to have a problem. But there's a 2.5% chance. The electricians said that, 10 years ago this happened and it failed fairly rapidly. Okay, well, the way this works is that everything gets summed up. You take the cost for the best case scenario, and we multiply that by 0.85, and we can see that comes up to $2,805. Okay, and we take the medium case scenario, 12.5%, and that comes up to $18,000 worth of avoided costs, and the worst case scenario. That comes up to $125,000 worth of cost. And you say to your management, to your customer, well, this one picture saved us $146,000. And they go, huh? Really? And management goes, oh, no, I can't believe that at all. And so you say, okay, and that's where we go back into that circle. And our management doesn't agree, so we have to go up and say, managers, customer, assign your own probabilities. And so here's the same chart with a best case scenario at 98%. We know that the worst case scenario can't be 0. Okay, it's going to be some number, and you can make as small numbers you want. And therefore, the best case scenario here, this would be a savings of $11,000, which is still pretty significant. Now, I've added in a spot down through here where you can actually track this if you wish. You can actually total up the total cost of repair. Okay, so we make an avoided cost guess, and then we take the total cost repair, and then we subtract it, and then we can track a net avoided costs. And this is a great way to do this. And are these numbers believable? Well, that's up to the individual company. That's up to the individual management to believe it or not. But this answers the question: what could this have cost had we not gone out and done our inspection? And so I think this is a pretty clever technique. So the examples here are kind of typical. Sometimes small anomalies can yield large numbers and make management question the results. Okay, early on in my career, when we created this program, this spreadsheet here, I found a 10-degree Celsius temperature rise, and the company itself calculated $980,000 worth of avoided costs. And I still think that was rather conservative based on what could have happened with that. Okay, so it's usually easy to determine costs associated with labor and parts. So the unknown is always the probability of failure. And it's not impossible. Sometimes people have a gut feeling, and an electrician, a mechanic, or a planner, an engineer, they know those systems. They know what has failed in the past and what probably what would happen in the future here. And then, of course, we have to work with our management, our supervision, and just assign the probabilities. But again, It's got to be between 0 and 100%. Something is going to happen, okay? And the best method is to try this out at your facilities. Try this out with your customers and track it and yeah, feed back to us whether this is worthwhile or not. But it's been used in certain industries for quite some time. Okay, so as a summary here, calculating return on investment for condition monitoring program is not impossible. It's somewhat difficult. But neither ISO 18436, which is condition monitoring, nor ASNT CP 105 or 106 curriculum mention return on investment. Okay, so the certification standards that we have out there for infrared thermography, and of course the other lubrication and vibration and ultrasound, etc., they're focusing on the technical topics required for certification. Okay, and so there really isn't any place in the curriculum for us as a training organization to add this in. But hopefully this webinar has been helpful to you. And it's up to individual companies. You can say, hey, this is great, or no, this is fantasy. It's entirely up to you. There will be a link to the avoided cost calculation spreadsheet here. Please use that. Please get in touch with me if you have any questions. And hopefully you can make and thank you. Thank you for your attention. Hopefully this has been helpful to everybody. Here is my contact information. Would love to hear back from you. It's Ronald Lucier, the Teledyne Infrared Training Center, 110 Lowell Road, Hudson, New Hampshire, 03051 in the United States. And there's my cell phone, 978-764-7020. And if you want to drop a note, say hi, whatever, it's ron.lucier@teledyne.com. Thank you, and I wish you all a wonderful day.